Ladies and gentlemen, welcome to this lecture on the fundamentals of regenerative braking. In this lecture, we will look at what regenerative braking is and its advantages and limitations. We will then see how to calculate the regenerative braking power and how the vehicle's speed and braking energy influence it. Finally, we will learn about what one pedal driving is. When we brake to slow down or stop in a conventional vehicle, the vehicle's kinetic energy is converted and dissipated in the form of heat by the mechanical braking system. In other words, this energy cannot be reused. On the other hand, regenerative braking is a process of recovering part of the vehicle's kinetic energy and converting it to a form that can be stored and used later. Electric cars are unique in their ability to implement regenerative braking. Under normal driving mode, the power flows from the battery pack to the alternating current AC electric machine via the DC to AC motor drive and an optional DC to DC converter depending on the battery voltage level. However, during regenerative braking, the electric machine is operated as a generator to convert the kinetic energy to electrical energy, and the DC to AC and DC to DC converters are used to store this energy in the electric vehicle's battery. Hence, it is necessary to have bidirectional power electronic converters which interface the battery and the electric machine. The key advantages of regenerative braking are threefold. First, regenerative braking reduces the energy consumption and therefore increases the efficiency of the vehicle, as part of the kinetic energy can be recovered and used later. Second, an electric car with a higher efficiency leads to a longer range of the car for a given battery size. Third, regenerative braking reduces the wear and tear of the mechanical brake pads or brake shoes, resulting in a longer lifetime of the mechanical brakes. The power delivered by the powertrain can be calculated for a simple one-dimensional analysis as per the formula shown. Here, the first two terms in red represents the rolling resistance force and the aerodynamic drag force respectively. These two terms are always positive, which means that they consume power from the powertrain. On the other hand, the gradient forces shown in blue and the vehicle acceleration forces shown in red can be positive or negative depending on the gradient angle and the change in the velocity dv by dt respectively. When the net tractive power P tracked is less than 0 or negative, the vehicle is under braking conditions and part of the power can be recovered using regenerative braking. It is crucial to note that it follows from the formula that a vehicle slowing down, that is dv by dt less than 0, does not imply that the powertrain is under braking conditions or P tracked is less than 0. Regenerative braking is crucial in urban driving conditions. The figure shows the speed variation as a function of time in the FTP75 urban driving cycle with frequent stop-go patterns owing to traffic and stoplights. Depending on the drive cycle considered, the braking energy can be 35% to 85% of the total traction energy. Hence, it is crucial to understand how braking energy and braking power vary with respect to the vehicle speed for the design of the regenerative braking system. Let us look at the percentage distribution of the braking energy with respect to the vehicle speed for the FTP75 drive cycle. Below speeds of 15 km per hour, the braking energy for a typical car is minimal and usually less than 15% for most urban driving cycles. Hence, regenerative braking is generally deployed only after exceeding a certain threshold speed, and normal mechanical braking is applied at lower speeds. Further, electric machines generate a lower voltage at lower speeds, making it challenging to recover the braking energy efficiently. If you look at the braking power required, due to safety considerations, a car is expected to be able to stop in a very short time than it is expected to go from 0 to 100 kilometers per hour, for example. In other words, the maximum braking power is usually much larger than the maximum power the vehicle can produce for vehicle acceleration and propulsion. The graph shows an example of the braking power distribution versus vehicle speed for the FTP 75 urban driving cycle compared to the power speed characteristics of an electric machine shown by the red line. Hence, depending on the machine's power rating and its base speed, not all the braking power can actually be recovered. So, regenerative braking systems are always used in combination with a mechanical braking system. There are several critical considerations for the design of the regenerative braking system. First, the braking system must produce the right amount of braking force to decelerate the vehicle according to the driver's needs. Second, how the braking forces should be distributed between regenerative braking and mechanical braking for various operating conditions must be investigated to recover as much energy as possible. Finally, how must the braking forces be distributed between the front and the rear axles of the vehicle? Different types of regenerative braking systems exist, such as series of parallel regenerative hybrid braking systems and the more recent use of torque vectoring to control the torque of individual motors connected to each wheel of an electric vehicle. Let's look at the simple implementation of a parallel regenerative hybrid brake system. The vehicle controller determines the braking force and the mode depending on the vehicle speed and the required deceleration rate. While braking, if the vehicle speed is lesser than the threshold, only the mechanical brake is activated. At speeds greater than this threshold and when the deceleration is less than a set point value, the electric regenerative braking system is used exclusively. Further, when the deceleration required is larger than the set point, both the mechanical and regenerative braking systems are deployed. An interesting implementation of regenerative braking by using only the acceleration pedal in the car is called one-pedal driving. For accelerating, a high pressure is applied on the accelerator pedal. But once the pressure is reduced, the vehicle will smoothly transition to coasting and eventually brake gradually when the pressure is further reduced or removed. However, one-pedal driving is generally used for gradual braking and not for emergency braking. Finally, let's look at the critical limitations of regenerative braking. Regenerative braking is limited by the power and speed range of the electric drivetrain, especially the electric machine. This means it cannot exclusively be used for all driving conditions and is always combined with mechanical braking. Thirdly, when the battery pack is almost full, additional charging via regenerative braking is limited or not possible. Finally, regenerative braking is limited only to that axle to which the electric machine is also connected. So, to summarize, we have learned what regenerative braking is and its benefits and limitations. In particular, we learned how to estimate the braking power and saw the energy and power characteristics for the urban drive cycles. Finally, we look at the essential criteria for the design of a hybrid braking system that combines electric and mechanical braking. I thank you for your attention.